In this video, I'm going to talk about rational functions and horizontal asymptotes. These are otherwise known as limits at plus or minus infinity. We can talk about horizontal asymptotes for different kinds of functions as well, but rational functions are the simplest example. We alluded to this in the example at the end of the last video over infinite limits and vertical asymptotes. So we're going to start by reviewing and summarizing that and looking at the graph on desmos.com and then talking about why we would expect a horizontal asymptote and for this particular function and how we can compute that just with pencil and paper in our own minds without actually having to look at the graph on a graphing calculator. Basically how we can come up with the graph ourselves without having to use technology to graph it for us. So let's look at the graph on desmos.com. Oh, actually, before we do that, this is what we talked about last time. We said, okay, if I take this function and I simplify it, I factor the numerator and denominator. In this case, it's already factored. Those two factors reduce. Because that factor reduces, the resulting function is well-defined at x equals 2, where the original function wasn't. So we're going to have an open circle at x equals 2 and the value of the limit. If we substitute x equals 2 in here and here, we get f of x is approaching negative 5 divided by 3. We actually get 5 divided by negative 3, so we get that. So that's our open circle. We know that the limit exists, but the function's undefined there, so we get that hole in the graph for an open circle. And then we said last time that because of the sign of this denominator as x approaches 5, we get 0, but 0 is tiny and positive to the, or even the denominator is tiny and negative to the left of 5, the tiny and positive to the right of 5. And because of that behavior, when we evaluate this quotient, we get a positive infinity and a negative infinity from the right and left respectively. And then I alluded to this, I just told you that it was true, but we'll talk about calculating that it's true in a minute. So let's look at the graph on Desmos now. So here's the graph. And I had to do a little bit of work beforehand to make sure that this would show up the way we want it to show up. We've got this function, and I know that the vertical asymptote is x equals 5. That's that line that the function gets very, very close to, vertical line. And then we had a horizontal asymptote y equals 1. I just told you that was true. And we have this open circle at x equals 2, y equals negative 5/3. So the limit from the left and the right of x equals 2 is negative 5/3. The y values approach negative 5/3, and we have the open circle there. And then as x goes to negative infinity, the y values as x goes to positive 5 from the left, the y values go to negative infinity. And as x goes to positive 5 from the right, the y values go to positive infinity. Now, when we talk about horizontal asymptotes, we're saying, well, what happens to this function as x goes to positive infinity? So as x gets very, very large, what do the y values approach? Or as x gets very, very small, very, very large in magnitude, but with a negative sign, what do the y values approach? And I told you that the answer was y equals 1, and I graphed the line y equals 1 here. We can see that that curve is approaching y equals 1 as we approach, or as x goes to positive infinity on the far right and x goes to negative infinity on the far left. We might wonder, like, how can we figure that out just by looking at this function? How could we draw that graph ourselves without the calculator? And I'll show you how to do that on my paper. So we're interested in the limit of this particular function as x approaches infinity. And if we're not in the vicinity of 2, we can just reduce those factors. And we've got an x plus 3 over x minus 5. Now, as x goes to infinity, if x is a very large positive number, this is a large positive number plus 3. And the denominator is a large positive number minus 5. So if x is 1,000,000, this is 1,000,000 plus 3. And in the numerator, we have 1,000,000 plus 3. And the denominator, we have 1,000,000 minus 5. That's very, very close to 1,000,000. That 3 is almost is very insignificant as x gets very, very large. And that negative 5 is also very insignificant as x gets very large. So I think, the answer should just be 1. I got basically 1,000,000 divided by 1,000,000. So I would assume that that function is approaching 1. But how can we prove that? Well, we call this an infinity over infinity indeterminate form. because the numerator and denominator are approaching infinity. In order to get rid of the infinity over infinity indeterminate form, we need to divide. Now we're going to have a tendency to divide by the highest power of x in the denominator, so that the resulting function in the numerator and the resulting function in the denominator, they usually will have a finite limit, but we really want that function in the denominator to have a finite limit. Since the largest power of x in the denominator is just an x to the first, we're going to divide the numerator and denominator by x. So we'll have the limit as x goes to infinity of x divided by x, which is 1, plus 3 divided by x, divided by x, which is 1, minus 5 divided by x. Now here, we'll have 3 divided by a very large number, and 5 divided by a very large number. Well, 3 divided by 1,000,000 is very, very small. It's getting closer and closer to 0. If x is 1,000,000, it's 3 over 1,000,000. If x is 1,000,000,000, it's 3 over 1,000,000,000. Like it just keeps growing. As x keeps growing and growing, this fraction gets smaller and smaller. So as x goes to positive infinity, this goes to 0 and this goes to 0, and we get 1 divided by 1, which is equal to 1. So the y values on our graph are approaching 1 as x goes to infinity. So y equals 1 is a horizontal asymptote of our function. But the y values are going to get very, very close to 1 as x goes to infinity. And you might say to yourself, okay, well, what happens as x goes to negative infinity instead? Well, I'm going to handle it in pretty much the same way. Divide by the numerator and denominator by the highest power of x in the denominator. And then I'm going to have this expression of 3 divided by a large negative number. So 3 divided by negative 1,000,000 is going to be a very, very small negative number, but it's going to be approaching 0. And then I'll have negative 5 divided by a large negative number. Negative divided by a negative is positive, but it's a tiny number. And it's approaching 0. As this number gets larger and larger in magnitude, the quotient gets smaller and smaller. So the limit as x goes to negative infinity is the same. So we still have the y equals 1 horizontal asymptote as x goes to positive or negative infinity. So let's look at that on Desmos. So we've graphed y equals 1, and we can see as we go to the far right, as x gets larger and larger, so here's x equals 25, the y values on the graph are getting closer and closer to that dotted purplish line, sort of magenta colored line. Is it magenta? I don't know. Purpley. And then as x goes to negative infinity, the y values on the graph are slightly less than 1, but they get closer and closer to that line. And so that is just an illustration of what we have right here. So let's review what we talked about last time. When we're graphing a rational function, if we have a common factor in the numerator and denominator, we want to reduce that factor as much as possible. Or we want to factor the numerator and denominator, excuse me. And then reduce as much as possible. So reduce any common factors. Now, if a factor reduces completely, so it's no longer present in the numerator or denominator after you cancel factors or after you reduce common factors. The limit of the function exists at that point. And it's equal to the limit of the simplified function. So for example, we said, here's f of x that equals x minus 2 times x plus 3 divided by x minus 2 times x plus 5. This function and this function are very similar to each other. I think that was a minus 5 instead of a plus 5. The only difference between this function and this function is that this one has a hole in it at x equals 2 and this one doesn't. So the limit of this function is equal to the value of this function, and the value of this function at x equals 2 is 5 divided by negative 3. So we get that negative 5/3. Excuse me. They're very similar. This one has a hole and that one doesn't, but otherwise the graphs are going to be exactly the same. They're exactly the same at every other x value, except for x equals 2. Now, if the denominator is equal to 0 at a particular x value, and the numerator isn't, then we have a non-zero number over 0, and that limit's going to be plus or minus infinity. And to figure out the sign, excuse me, of that infinite limit, we just look at the factors of the numerator and the denominator. We're looking at the signs of the numerator and denominator as x approaches c. So the denominator is going to approach 0, but we have to think about whether that's going to be a tiny positive number or a tiny negative number, and that will determine that sign there. Now these infinite limits, excuse me, correspond to vertical asymptotes. So if we get positive infinity or negative infinity, we know we've got a vertical asymptote there. And if a factor reduces completely, then our graph has a hole in it at that value of interest. So in general, it would have a hole at x equals c, y equals l, where l is the limiting value. Okay. Now we want to talk about horizontal asymptotes. We looked at a specific example. But let's do more. Let's look at something more general. The limit as x approaches c of a times x to the n plus b times x to the n minus 1 plus some lower degree terms plus some constant eventually. And then we'll have a different polynomial down here. I'll add, let's call this a sub n. Call this a sub n minus 1. And I'll call that a sub 0. And then here I'll use b sub n as the coefficients for my polynomial in the denominator. So b sub n times x to the n plus b sub n minus 1 times x to the n minus 1 plus other terms. So the a sub n and b sub n, those are just coefficients, they're just numbers. Don't let the subscripts bother you. The n just tells you that we're talking about the coefficient of x to the n. So if this is an x cubed, we call this b sub 3, but we're just talking about the number in front of the x cubed. Actually, let's use m here. That's an M instead of an N. Well, if if the degree of the numerator and denominator are the same, we're going to have a horizontal asymptote. If the degree and the numerator and denominator are different, well, it really depends on the relationship between this degree and this degree. So we looked at this example, the limit as x approaches plus or minus infinity of x plus 3 over x minus 5. We had the x minus 2's as well, but they don't affect the behavior as x goes to positive or negative infinity. We said that the answer was 1. And we said that the answer was 1 because the degrees were the same. First, it started out as an infinity over infinity indeterminate form. But if we divide the numerator and denominator by x, we can get rid of that infinity over infinity indeterminate form. I know we've already done this. So the limit as x goes to plus or minus infinity over 1 plus 3 over x divided by 1 minus 5 over x, and we just get 1. Now, in general, if those were the same, or if the exponents were the same, we might have something like this. Let's say we have like 3x squared minus 2x plus 1 divided by 4x squared plus 2x minus 5. Well, again, in order to figure out what happens as x goes to positive or negative infinity, we're going to divide the numerator and denominator by the highest power of x in the denominator. When we do that, it gets rid of the infinity over infinity indeterminate form. As x goes to positive infinity, this 3x squared is going to dominate. It's going to determine the end behavior. It's going to determine what happens as x gets very large, because 3 times a million squared is much, much greater than negative 2 times a million. Even though negative times a million is a lot, a million squared is much more than that. So this really determines the end behavior. And the same is true with this one. If I plug in a million, 4 times a million squared is much greater than 2 times a million. So these are the terms that determine what happens at the end. Now, as x goes to positive infinity, I take a large positive number and square it. So I'm going to have a positive number times 3. So this is, the numerator is going to positive infinity. And then as the same thing is true for the denominator, a large positive number squared is still positive, times 4 is still positive. So we have an infinity over infinity indeterminate form. But we can get rid of that by dividing by the highest power of x in the denominator. You divide every term by that. And then we simplify. X divided by x squared is going to leave us 1x in the denominator. 1 divided by x squared leaves us with that. 4x squared divided by x squared is just the 4. We have that. And so we have this. So as x goes to infinity, this guy's going to go to 0, and this guy's going to go to 0, this guy's going to go to 0, and this guy's going to go to 0. They all go to 0. And so we just get 3 over 4. So you say, well, what does that tell us about the graph? Well, if the y values on the graph are approaching 3/4 as x approaches positive or negative infinity, then we're going to say that y equals 3/4 is a horizontal asymptote for that function. So I don't know what the whole graph of the function looks like, but I do know that as x goes to positive or negative infinity, the y values are going to approach this horizontal line. Y equals 0.75 or 3/4. They might say, okay, that's what happens if the degree of the numerator and denominator are the same. When we divide by the highest power of x in the denominator, we just end up with a limit that's the ratio of the leading coefficients. So I see that these are the same. I see that this is a degree 2 polynomial and this is a degree 2 polynomial. So I know that the horizontal asymptote will have an equation y equals 3/4. But I don't want you to memorize that. I want you to think about how we would derive that answer. Think about this as an infinity over infinity indeterminate form, and then think about why that infinity over infinity determinate form could be determined. We could get rid of the fact that it's indeterminate by dividing by the x squared. That gives you the right answer. So let's look at what would happen as x goes to positive or negative infinity if the degrees of the numerator and denominator were not the same. So maybe we've got a 3x squared minus 2x plus 1. And maybe rather than having a 4x squared there, we've got a 4x cubed plus 2x minus 5. Now the degrees of the numerator and denominator are not the same, so we might not get a finite answer. But we're going to handle it in the same way that we handled it before. We're going to divide by the highest power of x in the denominator. Highest power of x in the denominator is that x cubed, so we divide everything by x cubed. We have 3x squared divided by x cubed, just leaves us 1x in the denominator. One of those x's reduces for the second term, so we have 2 divided by x squared plus 1 over x cubed in the numerator. And then 4x cubed divided by x cubed gives us a 4. And we divide each term by x cubed and simplify where we can. Now we've got that. Now think about what happens as x gets very large. 3 over a very large number is a very small number, so that's going to 0. This is also going to 0. That's also going to 0. Anytime you've got a constant divided by a very large number, a number that's going to be very large as x grows and grows and grows, that expression is going to go to 0. And the same is true here and here. So we end up with 0 divided by 4, which is 0. And you say, well, what does that mean? That means the y values on the graph of this rational function approach y equals 0. So y equals 0 is a horizontal asymptote for this function. And you might say, isn't there a shortcut? Do I have to do this every time? Well, you can memorize this rule, but I would prefer that you don't memorize the rule. This is an infinity over plus or minus infinity indeterminate form again. Because as x goes to positive infinity, this term dominates. So we're going to have something that's very, very large. As x goes to positive infinity, this term dominates these other terms. So this is going to be very, very large. So we're going to have infinity over infinity. The question is, well, if they're both going to infinity, which one gets to infinity faster? Does this go to infinity faster? So you have a finite number divided by something that's very large, where you get the answer of 0. Does this go to infinity faster, where we have a very large number divided by a finite number and we get infinity? Or do they approach infinity at approximately the same rate and get some finite number between 0 and infinity, like this case? Well, if the degree of the denominator is larger than the degree of the numerator, turns out that we're always going to get 0. And we can see why that happens. When we divide by the highest power of x in the denominator, we end up with one just constant term, and then a bunch of other terms in the numerator and denominator that go to 0. So these guys go to 0, these guys go to 0, and we have 0 divided by 4, which is 0. Or in general, you'll have a bunch of terms that go to 0 in the numerator, plus some constant, non-zero constant, plus a bunch of terms that go to 0. And then you'll have 0 divided by a non-zero constant, which will give us 0, in the case when the degree of the numerator or degree of the denominator is greater. You can almost think of it by just like ignoring those terms and say, well, what happens there? Well, an x squared and an x cubed, if you reduce that, you'd have a 1 over x. And 3 divided by 4x, if you will. 3 divided by 4x, obviously, is going to go to 0 as x goes to plus or minus infinity for the same reason that all of these guys go to 0. So that's another way to think about it. I prefer to work with every term in the expression or in the rational function. Now we've got 3 cases. We talked about the case when the degrees were the same. And we talked about the case when the degree of the denominator is larger. Now we could also talk about the case when the degree of the numerator is larger. So we've got the limit as x goes to plus or minus infinity of, was that 3x? Let's make that an x cubed now. So we've got that. Well, again, as x goes to positive or negative infinity, what happens to the numerator? Well, if x is going to positive infinity, I've got a very large number cubed times 3, which is a very large number, so we get positive infinity for the numerator. And then if x is going to negative infinity, a very large negative number cubed is negative, and then you multiply it by a 3, so it's still negative. So we get plus or minus infinity, depending on whether we're approaching positive or negative infinity here. The denominator, if x is a large positive number or if x is a large negative number, it doesn't matter. If we square it, it's still positive. So we get a large positive number times 4. It's going to positive infinity. And so we have this negative plus or minus infinity over infinity indeterminate form. And you say, okay, that's indeterminate. What's going to happen as x goes to positive or negative infinity? Can we figure it out? Turns out we can. If we divide the numerator and denominator by the highest power of x in the denominator, three x cubed divided by x squared gives me a 3x. We'll take this and divide it by x squared. One of the x's will reduce. As x goes to infinity, this term goes to 0, this term goes to 0, this term goes to 0, and this term goes to 0. So now I've got an expression, 3x divided by 4, and I want to know how that expression behaves as x goes to positive or negative infinity. As x goes to positive infinity, I've got 3 times a large positive number divided by 4, which is going to give me positive infinity. And as x goes to negative infinity, I have 3 times a large negative number divided by 4, which is going to be negative infinity. So I write plus or minus infinity here. Note that the sign designation, the plus and minus, goes with this sign designation. So as x goes to positive infinity, the answer is positive infinity. As x goes to negative infinity, the limit is negative infinity. And in this case, the function does not have a horizontal asymptote. But we do know that as we look at the graph as x goes to the far right, as x goes to positive infinity, the y values are going to go to positive infinity. And as x goes to negative infinity, the y values are going to go to negative infinity. So we can talk about what's called the end behavior of that rational function. Let's look at some of these functions on Desmos.com to verify our calculations. Okay, so we looked at these 3 examples where we had f of x equals 3x squared minus 2x plus 1. That was in the numerator, and g of x equals 4x squared plus 2x minus 5 in the denominator. And then we said, well, what's the limit of that function as x goes to positive and negative infinity? Well, since the degree of the numerator and denominator are the same, we did a little bit of algebra. We divided the numerator by x squared, and we divided the denominator by x squared. We said the limiting value was 3/4. I've graphed that function here, h of x, and I've graphed the horizontal line y equals 3/4. It's that green dotted line. And I think you can see that as we approach, or as x gets larger and larger and larger, that purple line gets closer to the green line. It actually gets so close that they look indistinguishable on Desmos.com. And the same is true as x gets smaller and smaller and smaller. So larger in magnitude, but farther to the left, more and more negative. That graph gets very close to that value. And then we said, okay, what happens, or what does the graph look like as x, or if we change the degree of the numerator and denominator? Let's say we change the denominator to a 3, or the degree 3, but otherwise the graphs stay the same. Well, in that case, y equals 3/4 is not the limit. We end up with y equals 0 as the limit. We divide the numerator and denominator by x cubed, we end up with a bunch of terms that go to 0, divided by 4, plus a bunch of other terms that go to 0. So the limit is 0. And I graphed the line y equals 0, which is just the x-axis. And we can see that as x goes to positive infinity, that graph gets closer and closer to the x-axis. And as x goes to negative infinity, that's farther to the left, the y values get closer to the x-axis. So it's exactly what we would expect. And then we said, okay, well, what happens as if we make the degree of the numerator larger? So I'll make that a 3 and keep that as a 2. And then we end up with this graph. And say, oh my goodness, that's actually kind of interesting. Since the degree of the numerator is actually 1 more than the degree of the denominator, we don't have a finite limit. It turns out that as x goes to positive infinity, if we divide the numerator and denominator by x squared, we get a 3x as our leading term. Every other term goes to 0. in the numerator, and we get a 4 plus a bunch of terms that go to 0 in the denominator. So the function behaves a lot like 3/4 x. So let's graph y equals 3/4 x. That's called, or that's what we call a slant asymptote. We don't cover that too often in this class, but the graph gets very, very close to this line, y equals 3/4 x, as x goes to infinity, as we can see. As x goes to positive infinity, the y values go to positive infinity, and they get close to that line. And as x goes to negative infinity, the y values go to negative infinity, we get very close to that line. But the limits themselves are not finite. As x goes to positive or negative infinity, we get positive or negative infinity as our resulting limit. Now you might be asking yourself, well, there's some other interesting things happening here. We have some vertical asymptotes as well. And we had vertical asymptotes as well when we were looking at the first example, where we've got that x squared term and that x squared term. You might say, well, how can I find the corresponding vertical asymptotes? Well, in order to do that, I would need to factor the numerator and denominator as much as possible, cancel any common factors where we have some, and then I always like to graph the vertical asymptotes with the graph as well, and you can see that the graph is getting close to two vertical asymptotes here and here. Now let's do that on our paper and then graph the corresponding vertical asymptotes. All right, so here we are. Now to find the roots of these functions, or the factored form of these functions, we need the roots. We need to figure out what x values would cause these functions to be 0. If x equals 0 is, or excuse me, if x equals k is a root of the function, or 0 of the function causes the y values on the graph to be 0, then x minus k is a factor. Of f, provided that we're talking about a polynomial f. Now, with these two functions, it's not obvious. These aren't functions that factor really nicely. The numerator actually might factor nicely. Let's see. Now, because I've got a number other than 1 in front of that x squared, we might use what's called the AC method for factoring, also known as factoring by grouping. I said graphing, grouping. I'm going to switch to blue because my black pen is running out. So rather than looking for two numbers that give us a product of the last term and a sum of this middle term, we're looking for a product of a times c. In this case, if this is ax squared plus bx plus c, a times c is 3 times 1. A is 3, b is -2, and b is 1. We want a sum of -1, or excuse me, sum of that middle coefficient, sum of -2. Now, are there any two numbers that give us a product of 3 and a sum of -2? And they don't. We can't find any x values that do that. So you might say this can't be factorable. Say, well, if it is factorable, like how would I find the roots? Maybe the factors are just irrational numbers. Well, you could just set this equal to 0 and solve, because the definition of a root of a polynomial is just an x value that causes that polynomial to be 0, and that can be solved using the quadratic formula, that x equals -b plus or minus the square root of b squared minus 4ac, all divided by 2a. If b is -2, we've got the opposite of -2, which is 2, plus or minus the square root of b squared, so that's 2 squared, minus 4 times a times c, all divided by 2 times a. And so we've got 2 plus or minus the square root of 4 minus 12 divided by 6, which is 2 plus or minus the square root of -8 divided by 6. The square root of 8 is the square root of 4 times 2, so square root of 4 is 2. Square root of 2 can't be simplified, so we'd write that there. Since that's a negative, you get an I outside. And then you divide all of this by 6. So the roots of this polynomial are complex numbers. That means that we could factor this in the complex number system, but we can't factor it in the real number system. So if I wanted to factor it in the complex number system, I would have x minus c1 times x minus c2, where c1 and c2 are these two answers. So I'd have x minus 2 plus 2 root 2 times I over 6. And then x minus quantity 2 minus 2 root 2 times I over 6. And of course, you could simplify these further. You can factor out the 2, cancel the common factor with the 6 in the denominator. You can simplify, but I don't want this factored form. I want a factored form if possible, but I only want it in the case when these are real numbers rather than complex numbers. So this does not factor in the reals. If I draw the polynomial itself, it turns out that that graph is going to be above the x-axis the whole time, so it doesn't have any roots, and not any real roots anyway. So this does not factor. We can do the same thing with that 4x squared plus 2x minus 5. Set that equal to 0 and solve for x. Get negative b plus or minus the square root of b squared. B is 2 minus 4 times a times c. And we get negative 2 plus or minus the square root of 4. And I have negative and a negative, that's going to be a positive. That's 20 times 4 is 80. So I've got negative 2 plus or minus the square root of 84 divided by 8. And those are irrational roots. So that one actually does factor. 84 is 4 times 21. 21 is 3 times 7. That doesn't have any other perfect square factors. Square root of 4 is 2. Square root of 21 can't be simplified. And I've got all of that divided by 8. So let's divide this by 8 and that by 8. And so we get negative 1/4 when we reduce, and plus or minus square root of 21 divided by 4. So we actually have two roots. X equals negative 1/4 plus the square root of 21 over 4, and x equals negative 1/4 minus the square root of 21 over 4. Now the square root of 21 is in between the square root of 16 and the square root of 25. So this number, square root of 21, is between 4 and 5. So I've got negative 1/4 plus some number that's between 4 and 5 over 4. And then I've got negative 1/4 minus some number that's between 4 and 5 over 4. So this is somewhere in between 1 and 1.25 approximately. And we are taking that and we're subtracting 0.25 from that. So those are actually going to be the vertical asymptotes of our function. Say, how do you know that again? Our numerator does not factor in the real number system. And our denominator does factor in the reals. And we actually have to multiply by a 4 to make it actually equal to that. It's going to be the leading coefficient 4 times x minus the first root times x minus the second root will give us this. The first root is that negative 1/4 plus square root of 21 over 4. And the second root is negative 1/4 minus square root of 21 over 4. And of course, we would simplify that if we wanted to. But those correspond to the vertical asymptotes. So to see that, let's look at the graph on decimos.com again. Okay, so we said x equals, oops, sorry about that, x equals negative 1/4 plus square root of 21 over 4. It's one of our asymptotes. I like to make it dotted. And then the other one's gonna look just like it, except we're gonna have a minus there. These are just the roots of the denominator. Now you might say, well, how do you know that you get two asymptotes? Well, we looked at the picture and we could tell that there were two asymptotes. But we also know that there are two asymptotes because we said if we take 3x squared minus 2x plus 1 and we set it equal to 0 looking for roots, we get complex numbers. You might say, is there an easier way to show that you get complex numbers there? And well, the answer is yes. Let's look at the graph of this 3x squared minus 2x plus 1. We could complete the square and figure out where the vertex of the parabola is. We know since the 3 is positive, it's a parabola facing up. But if we look at the graph, we can see the parabola never crosses the x-axis. So its roots are complex numbers. We found those on our paper. Let's look at g of x. G of x does cross the x-axis at about there, approximately negative 1.396, and there, x equals 0.896. And if we do the calculation by hand, and then we type those functions or those expressions in for x, we get the same values for x. X equals 0.896 approximately, and x equals negative 3.956. So those two roots correspond to those vertical asymptotes on the rational function here. And then we've got the horizontal asymptote as well. So we've got vertical asymptotes where the denominator is 0 and the numerator isn't 0. And we've got a horizontal asymptote horizontal asymptote that's non-zero because the ratio of the leading coefficients is 3/4 and the degree of the numerator and denominator are the same. Now, in the case where we had a 4x cubed here, it looks like we've got one asymptote, and it's a little bit harder to see. When you look at that expression, it's not obvious how that function factors, if it factors at all, the function g of x. So we might look at the graph of g of x again. And we see that we've got a root at 0.924 approximately. So x minus 0.924 should be a factor of this. And I'm not actually sure if it is a factor or if that's just an estimate. But we could use that to infer that we do get at least one real root, and then we would expect, it looks like the other roots must be complex. So this can be factored as x minus a constant, where that constant is either 0.924 or possibly an irrational number that is approximately equal to that. And then we're going to multiply by an irreducible quadratic. That's just a quadratic function that does not have real roots, or a quadratic function that when you graph it, it kind of looks like this. It just doesn't cross the x-axis. It's either entirely above the x-axis or entirely below the x-axis. But if we take that and graph 0.924, we see we've got that vertical asymptote right there. And we said that the horizontal asymptote, because the degree of the denominator was larger, when we divide by the x cubed, we end up with a 0 as our limit. So there's our horizontal asymptote and our vertical asymptote, and our graph roughly looks like that. Sorry, I'm trying to graph those. Vertical asymptotes again for this example. Now, if we change the degree of the numerator, we still end up with those same asymptotes in the denominator, or the same asymptotes due to the denominator being 0. When we graph the corresponding function, looks like that. And we said y equals 3/4 x is a slant asymptote. So as x goes to positive or negative infinity, the y values go to positive or negative infinity, but they do so in a way that's very similar to y equals 3/4 x. And it has vertical asymptotes when the denominator is 0 and the numerator is non-zero. You might say, okay, well, where is it equal to 0? Well, it's equal to 0 right there. That must be an x value where the numerator is 0, but the denominator is not 0. So let's look at this f of x, and see that that is equal to 0 at x equals -1. So I would expect x plus 1 to be a factor. And then when we take the quotient, we're going to have a 0 at x equals -1. So let's look at the quotient again. And it looks like we've got that 0 at x equals -1. All right. So here's a summary of what we talked about with regard to horizontal asymptotes. If the degree of the numerator is equal to the degree of the denominator, then y equals a sub n divided by b sub n is a horizontal asymptote. And that's because when we divide by the highest power of x in the denominator, we end up with a non-zero constant divided by a non-zero constant plus a bunch of terms that go to 0. And we do that to get rid of the infinity over infinity or plus or minus infinity over infinity indeterminate form. Now, if the degree of the numerator is less than the degree of the denominator, then y equals 0 is a horizontal asymptote. And that's because when we divide by the highest power of x in the denominator, we end up with a bunch of terms that go to 0 over a non-zero number. So we get 0 over the non-zero number, which gives us 0 as the limit. So the y values approach 0. And if the degree, the numerator is greater than the degree of the denominator, the rational function does not have a horizontal asymptote. The function value is going to go to either positive or negative infinity as x goes to positive or negative infinity. And that sign will be determined by the signs of the coefficients and the signs of the leading term of the degrees in the numerator and the denominator. Now, we just briefly mentioned this. If the degree of the numerator, or we saw an example of this, is the degree of the denominator plus 1, the function has a slant asymptote. That just means that the graph is going to approach a line as x goes to positive or negative infinity. So we're going to have a limit that is either positive or negative infinity, but it's, when you look at the graph, it's actually approaching positive or negative infinity in a very predictable way, very similar to the way that a corresponding line grows to positive or negative infinity at the extreme values as x goes to positive or negative infinity. We won't focus on that too much, but you did see it on the graph, and that's actually what it looks like. The function's going to look like a line if the degree of the numerator is 1 more than the degree of the denominator. And I think we can see why that's true, because as if we divide out the highest power of x in the denominator, we end up with a constant times x in the numerator, all divided by a constant.